Hi to all. Our next topic is energy consideration. We are discussing the electromagnetic induction chapter. In this, I am going to explain the energy consideration. What is energy consideration? That means here, this one we already discussed. This is a PQ conductor, right? This is a conductor PQ. This conductor is placed over the rectangle frame. This is also wire bent in the form of rectangle, and this PQ conductor is movable over this conductor, right? This is a naked wire without insulation, right? When it will move this conductor right side, in this current will be induced. Why? Because the area of the loop changes, the flux length changes, okay, because it is placed in the magnetic field. When we move this conductor right side, the area of the loop is increasing, the flux is increasing, the change in flux induces current and EMF in this. The direction of the current is given by the Fleming right hand rule. According to that, you have to stretch the forefinger, central finger, thumb mutually perpendicular to each other. Adjust the forefinger in the direction of the field is inward, and adjust the thumb in the direction of the motion of conductor. Then the current indicated by the central finger. Forefinger field, thumb motion of conductor, central finger induced current. Then the induced current is upward by this. Then current is upward. In this there is no battery, but the current generated, that current is upward. This PQ conductor across EMF generates, it will act as cell, but in the cell the current flows from negative to positive. That means this is negative and this is positive. Then what is the induced EMF? Induced EMF across PQ conductor. Across PQ conductor. Yes, we know already that one. Its magnitude is BLV. Okay. And induced current in the loop, right? Induced current in the loop. What is the induced current in the loop? Its formula is I. Induced current is equal to EMF by resistance. The total resistance of this loop we can take as R. Then that we write as BLV by R we write. Okay, right? This is equation 1 and this is equation 2. And now when the current passes through this, right, certain I current is passing through this wire, through this conductor, whose conductor length is L. Whenever PQ conductor, it carries current I, its length is L, it is placed in the magnetic field. On that, force will act. Whenever any current carrying wire, if it is in the magnetic field, it experiences the force. Then that force direction is given by the Fleming left hand rule. You remember that force on current carrying wire in the magnetic field is given by Fleming left hand rule. Force induced current direction is given by the right hand rule. Right hand rule gives the induced current direction. Left hand rule used to know the direction of force on current carrying conductor in the magnetic field. Then according to that, I want to know the force direction on the conductor, magnetic force, right? Then for that, you have to adjust the forefinger in the direction of the magnetic field, central finger in the direction of the current, then thumb indicates the force. Look at here, forefinger inward, central finger upward current, thumb left side. That means magnetic force on this conductor. Magnetic force on this conductor acts left side. This is the magnetic force, right? Now the magnetic force on the conductor, magnetic force on current conductor, right? Current carrying conductor PQ. Okay, on PQ conductor, how much force acts? That magnetic force is, we know ILB sin theta. ILB sin theta. Okay, L is the length and B is the magnetic field. Sin theta. Theta is the angle between the L and B. L and B are perpendicular. L is like this there, B is inward. They are perpendicular like this. Okay, like this. Then we write as ILB only because L perpendicular to B implies theta 90 degree. From this, the force we got it here, force, okay? magnetic force we got as ILV. In this, if you want, you can write the I formula as BLV also, right? If you write, then what you will get? The magnetic force. Okay. Now let us see. Magnetic force we will get as I is BLV by R into LV. We write the magnetic force as F suffix M, magnetic force, B square L square V by R. This is the magnetic force act on the wire. That force will act in the left side, right? This magnetic force F suffix M acts on PQ conductor in left side, right? Left side direction force will act. But we want to move in the right side. Then for that we have to apply the force right side. Okay. Then I want the power required to move PQ conductor with constant velocity. Power required to move PQ conductor with constant velocity. I want to move the PQ conductor with constant velocity right side. Then how much power required? How much muscle power required? I am moving, right? Actually, when you will move this side, then the opposition force is there. Then you have to apply the right side force that should be equal to opposition force. Then at the moment net force will be 0. The supplied force and the magnetic force will be cancelled. We want to move this conductor this side. Then the supplied force and the magnetic force will cancel. The net force is 0, means it can move with constant velocity. The power required formula is force into velocity, right? Force into velocity. Force we got here already, that is B square L square V by R into V. This is from equation 2. Then we will get the power. Final formula is B square L square V square by R. This is equation 4. And then this much power we are using to pull this side, right? And this power, where it gone? Now when the power required, how much power when you will use some power energy that converted into electrical energy, that is passes through resistor, it converted into heat energy. That means what is the power dissipated across the resistor? Power dissipated across resistor capital R. The power dissipated formula is I square R, right? We know already. Where I is from equation 1, that is BLV by R from equation 2. Right here we write. This is equation 3. From equation 3 we are writing the force formula, right? And B whole square into R. You simplify this, that is the B square L square V square by R square into R. This will cancel. Then power dissipated we will get as B square L square V by R. This is equation 5. From equation 4 and 5 we write one conclusion, that the power required to move conductor is equal to the power dissipated across the resistor, right? Both are equal. How much power you are using, that much power converted into heat energy. What are the energy changes occurred in this? Okay, energy consideration, energy changes, right? Energy changes occurred. What are the energy changes that occurred in this case? Okay, in this case, what are the energy changes occurred? That I want to know. That is, you know very well, you are using the mechanical energy, right? Kinetic energy you are using. Okay, that kinetic energy and the mechanical energy convert into electrical energy. Right, here we are using the mechanical energy. That mechanical energy converts into electrical energy. Then electrical energy passes through the resistor, then it converts into heat energy. These are the energy changes occurred, right, in the wire during this motion. Right, this is about energy consideration or the power consideration. Take the screenshot and note it. Thank you for watching my lecture. If you have any doubt, you can contact me in WhatsApp. Thank you.